Hi, it's Terry Dennery of the MathWorks. So in this video, we're going to kind of pursue again, we're going to really begin to concentrate on flight controls and not just introduction to controls. Right? And so we got this cool little vehicle aircraft we have. And so I'm going to kind of move it down there and rerun the animation. And this is really where we left off on the last video. It vertically takes off. And this was all produced by our Simulink model. And you can see we did pretty well. And so we have a blue line that's sitting right on top of a yellow line here. That's why it looks like we're only using one. And that yellow line is our command signal, which enters first. And the blue line is what our simulation tells will happen with the real vehicle, right? And the unofficial title of this video, I might call it this even as I post on YouTube, is Training Wheels. All right. And so perhaps you'll kind of get the idea as I kind of show this. And it's the fact that we mechanically constrained it. That's what this is. It's a prismatic joint. We constrained it so it can only move in a vertical direction. And we even made this measurement on the torque carried by that, showing that a torque is required to keep it vertically. All right, and all it really means is there's a coordination of our forward thrusters and our rear thrusters required to make sure that we do not impart a moment on it. All right, and so that's what we're going to kind of jump into now. All right, and so the way we're going to do it is to take the training wheels off. All right, and that really means kind of disconnect all this. All right, and so I'll move all this out of the way. I will right mouse click. I will comment it out, and I'll type on my background, just type in the number 6. You'll see the first thing that shows up is 6-stop joint. That's what we want. Okay, and I'm going to hook it up like this. And I'm going to zoom in real close on the joint itself even. You can see it's basically a ball with basically 3 lines passing through it. The idea is the ball is a completely rotational connector between kind of the ground and this vehicle, and therefore it can, and that the lines represent basically it's free to move in the X, the Y, and Z direction. So it's funny we call it a 6-stop constraint, but it really imposes no constraint at all. And it's through this that we're able to allow it to fly freely. And the movement's really because gravity is acting on the vehicle, but we also have 4 thrusters, and 2 in the front we call forward thrusters, and 2 in the back are front thrusters, and the 2 in the back we call rear. All right. Anyways, we've effected that change now, and so it's reset. Let's hit the run button right there, and you'll see without that kind of constraining moment, well, the whole thing's going to begin rotating. All right, and it's really not that hard of a problem to fix. And in a way, it's kind of like your first class in statics. It's very much like a simply supported beam. So I decided to map it out in PowerPoint, and so let's see how this goes. So let's hit the animate button. Okay, and so we know that basically there's a center of mass, and we know gravity kind of effectively operates through the center of mass. And so then if I hit a click, I'm going to add the thrusters. And so the rear thrusters are way back here, and the forward thrusters are not quite all the way to the front, but that's kind of what it is. All right. And so from this, we kind of know from sum of forces, that T front plus T rear, well, that should be equal to the mass times not only the gravity, but the gravitational acceleration. Right, so we get one equation, but we still got our 2 unknowns, T front and T rear. Right, and that means something because our arbitrary choice to just say, make them equal, well, that wasn't good enough. All right, and that generated a moment, and absolutely we saw that in the simulation. Right, and so it's kind of the acknowledgement that location matters, and so I introduced these new parameters, these variables, XR for the distance from the rear thruster to the center of mass, and then XF, the distance from the front thruster to the center of mass. And so if we take the moment equation and we choose a point of moments, well, let's choose that point aligned with the center of mass, and then we'll get this equation. And so x times t front minus xr times t rear, that'll be equal to 0. The sum of moments will be equal to 0. And with those two equations, we can solve for the unknowns. Okay, so now let's be a little more attentive to where this mechanical model come from, right? And so go to my favorite mechanical modeling tool called SimWise. And one of the reasons it's one of my favorite mechanical modeling tools is because it allows me to import quite easily into Simulink through the tool SimScape Multibody, which I'll say is one of my favorite mechanical simulation tools. All right, and so anyways, with SimWise, and perhaps I'll do an additional video where I'll really kind of get into the CAD import, but I'll just kind of acknowledge that this was drawn up inside a CAD tool. I believe it was SolidWorks, and we basically made our mechanical model from that. And that the mechanical model is more than just the shape, but it's the way it is constrained. And so you'll see it right there. There's that vertical constraint I was talking about. And so I'm going to grab this tool, the Move tool. And you'll see as I drag it up and down, it can move only in that one direction. I can't pull it forward. I can't move it left and right. Now you'll see that these constraints are made up of Cartesian coordinate systems. I'll zoom in on one right there. They're essentially defined in terms of x, y, and z coordinate axes. Right? So let's just get back to kind of a good kind of reference frame. All right, and I'll also point out this. Well, you can kind of see them in the back right there. There's our rear thrusters, really defined by a point location and a coordinate axis too, which is going to be good because this is a vertical takeoff vehicle where these thrusters will transition to an orientation which will allow them to drive, horizontal movement, just like real jet engines do. And of course, this thing's got flight control surfaces, and we'll get into the aerodynamics of lift and drag associated with them too. And you can actually see in our orientation right now, at least the green arrows are pointing in the direction that would propel horizontal thrust. But we're bringing it to Simulink. We're good with vectors in Simulink. We'll essentially load that up in the z direction. So those are our rear ones. Let's go here. Let's rotate the full vehicle. Let's look at it in wireframe. And there you'll see our two forward thrusters. All right, and let's get that back to 0. And that's our nominal position is when it's down there. All right. And so this cool flight vehicle, we'll bring that into Simulink now. And this is an app. It's an app that exists because MATLAB's good at doing apps. It's an app I wrote many years ago, but it's essentially a lot of MATLAB code that will work through the API of SimWise, gather all the information that defines that mechanism, which is mostly what are the bodies, the joints, and the coordinate frames, the things we're just looking at. And in terms of body, you get mass and inertia and stuff like that. Joints, it's usually kind of functionality. Is it a vertical constraint or is it a 6-dot? Is it a revolute or whatever? All right, and with that, okay, well, let's go figure this out. SimWise, why do we get to? Oh, okay. So here's essentially the tree structure for this entire vehicle. We talked about that. Here are the 4 thrusters. So we've talked about that. And you'll see that I actually marked a location, the center of mass location. And that this is something that we know because SimWise is good at calculating that. So I go to Assembly, Inertial Properties. There's the center of mass location. I simply typed in those X, Y, and Z. All right. And so that's really a good thing. So let's kind of see how we'll use that as we now kind of move forward. All right. And hopefully it's kind of clear from our previous model, that we kind of have the 4 thrusters going in right there. What you'll see what they're looking for are Well, in parentheses, it has a big N, a capital N, that stands for newtons, and essentially they're looking for thrust or force that's going to be expressed in newtons. All right, and so we're going to calculate that, and we're going to get this thing to work. All right, and so maybe I'll move that up there for right now. All right. So you know what I think I'll do? I think I will save that for a future video. And the idea of center of mass, as well as inertias and mass, and kind of gathering that information from a tool like Simulink, there's some kind of nifty or kind of cool ways to do that. But for right now, it's just going to accept that we know the answers right now. And so what I'm going to do is perhaps go back to SimWise. So let's just kind of get that information. And so we'll see that the rear thrusters, they're at a 0 position. All right, so that's kind of a convenient choice. It doesn't mean anything physical at all. It's just kind of our choice on nominally defining the location of important reference frames. And the most important is going to be the world reference, and that's that black coordinate frame right there. So that's our nominal definition because we chose to put the air vehicle at that location with this orientation. So anyways, we care about X. X is 0 for the rear thrusters. Let's go to the front thrusters. Get to the coordinate reference frame on that, 1.4. And then, again, kind of knowing where that center of mass frame is, seeing that position at 0.663, right? And so the XR and XF that are important to us, I'll just kind of do this in MATLAB. Well, it's going to be XR is center of mass from the 0 point, which is where the rear thrusters are. So we'll simply recognize XR is equal to 0.663. I believe, did I get that right? And XF is the forward position. It's 1.4 minus 0.663. Okay. All right. And so now let's go ahead and program this into our thrust calculation. And that here, actually it is here. Okay. Again, we're operating now. We're not going to be quite as simple here. So I'll kind of delete this here. And what I will do is already introduce kind of a demux. And demux basically means that the signal coming in is going to have two components. Right? And so one's going to be for the rear thrust. So those are the ones up here. Another one will be for the front thrust. That's a little bit of a bad notation thing, and we might revise it at some point and try to get the front ones on the top and the rear on the back. But for right now, that winds up with our model much nicer. All right, and so that's F going in now, and now we need to calculate that. And so how are we going to do that? Well, we're really good at inverting matrices. And so let's go into Simulink, user-defined functions, and let's get some of that MATLAB capability in. Okay, so anyways, we've already calculated that total thrust right there, and it's very convenient that it even includes that feedback. So if we're wrong or error develops, that we kind of get that restoring force, so we'll be contributing to it too. So that's pretty useful. So as you can see, we're really already kind of getting into the controls, and ultimately we're amending the controls to include this, I'll call it distribution of load between the front and back or rear thrusters. And we'll do that here. And we'll essentially do the equations we're just looking at in PowerPoint. All right. So this is all basically equal to the thrust, which has already been calculated, and we'll kind of solve those two equations. So we're going to solve essentially AX equals B, if you're familiar with that terminology. All right. And the total thrust is coming in. If AX is equal to B, well, that total thrust is what the first combination of forward and rear thrust, the forward plus rear, is going to be equal to that. And so we'll put in B is equal to that total thrust, all right, and we'll put a semicolon. This could be what we call a column vector. So that's going to be equal to the total thrust, and then the second equation is about the moment equation, which we want to be equal to 0, meaning that the combination of forward, rear thrust, and gravity will sum up to 0 moment. All right. So we got B done. Now let's get A. All right. And A times X will be equal to B. Well, X is basically forward thrust and then rear thrust. Right? And so the first row is 1, 1, meaning that they add up to the total thrust. And the second column is a little more complicated. It's XF times forward thrust, I'll put the comma in, minus XR times the rear thrust. Okay, and I'm going to call it the return variable. Let me just call it thrusts. I'll call it scalars. Yeah, you might call it, actually it's called thrust. Maybe we're overdoing it on names, but names do matter. Okay, so let's get thrust amps. All right, and so thrust amps, this could be the solution of the equations, which we're casually calling AX equals B. So it's really A times thrust amps is going to be equal to B, and therefore thrust amps is going to be equal to A, and this is the way we like to tell you in MATLAB, pre-divided. Oops. One of those guys, E. All right, and so that will be our output. All right, and that all looks pretty good. All right, and so got a little bit to do, and therefore I'm going to make a little bit of room here. We're certainly going to do this, and we're going to do a little bit more too. All right. All right, and that's why it's so specific about calling it thrust amps, because what we're looking for in here ultimately will be vectors that are really kind of defined at this level. We'll see the SimScape multi-body blocks looking for a vector definition. Right? And in this case, it's kind of straightforward, and that's because in vertical thrust, there's only going to be one non-zero component, and that's going to be Z. All right? And so here's what we're going to do is create a little subsystem. The mux block. And we'll add a third port. And we'll bring in a constant. That is not what I wanted. Okay. CONST. That's coming from my own library. I should have been a little more careful. All right. And anyways, we're going to just fill in X and Y values with 0. And package that in a subsystem. Make Z vector. Might come back and rename that, but for right now I kind of like that name. I'll call this Z comp, and coming out will be ZVec. Okay, and while we're at it, why don't we just kind of fix kind of the issue with kind of the backwards orientation, right? And so anyways, this probably will be a worthy subsystem too. All right, so let's bring in a demux. Each component will become a 3D vector. Let's mux it, but let's kind of do the cross now. And so could have done it in here too. I guess we could have just redefined it, whatever. And that's the nature of software. And certainly there can be better choices, and there could be better choices than what I've just made. But I think with that we do have it. And so with that, essentially all this is now my controller. Now let's go just kind of the initial rendition of our flight controller. All right. Like that's already calling it feedback. And here we'll call thrust and put plural with an S there. And that looks pretty good. And without further ado, let's see how we did. Oh, undefined XFXR. I thought that I had that in my workspace. XFXR. Well, that's kind of a simple one. Probably some cute, maybe a little bit clever ways to do this, but to kind of make this easy, I'm going to just send it into the function. And so I go XFXR. You can kind of see in my workspace that they do exist. The MATLAB function cannot see that yet, though. And so we'll make this a little bit more complicated. And I'll probably clean this up so it looks a little nicer, maybe in between videos. Probably throw all that stuff into a subsystem too. So let's get constant in there. And so this block can see into my workspace. And it brings up kind of an important consideration too. It's not all, where you want to put your data, actually, especially as you get into code generation workflows, can be I'd say very good choices can be made that probably are going to be other than putting it into the workspace. So anyways, with those XFXR, think we got it. Let's go ahead and try hitting run again. Okay, let's fix that. Okay, two things. All right, so just spent about 10 minutes kind of working through this. And so kind of a strange movement. The really strange thing is it kind of bouncing up and down, and the other thing is that it's kind of moving forward. And so the bouncing up and down, I think it's more strange, but that's really kind of the simple fix. All right, so let's get back here, and that there are 4 total thrusters, 2 front ones, 2 rear ones, and therefore this number being calculated just needs to be divided by 2. And I'll suggest the simplest way for right now is just introduce a gain. And make it 0.5. So that'll reduce them by half. All right. And you'll see when we hit run now, it still will kind of move forward. Okay. And I want you to look close. Here, let's zoom in real close. That it has a tilt. All right. And this is really me just not being, I'll say, attentive enough and probably being a little bit sloppy, and that you need to be precise on things like moment arm calculations, especially if you're not applying feedback that will kind of correct it. future video, we'll probably put a little bit of feedback in there, just make sure is, center of mass position, of course, will change quite a bit as you load the vehicle differently, and we'll kind of address that issue from a number of fronts, but one will be to add a little bit of feedback. So, anyways, going back to SimWise, I did more resolution on my numbers here, 0.663, 153, right? And so the 153 is important. And so let's get to MATLAB. You'll see I typed it into here, and then I also typed in this equation. I'm going to just copy these now. And let's put this into our live script that's calculating our data for us. And let's just make this part of the calculation. All right. I guess I like having a little space there. It's not negative XR, we're just subtracting it off. So let's hit run, and that recalculation is now in our workspace, and I think we got it now. I've said that before, so let's be careful of comments like that. And let's reset it again, like that, and let's make it small enough so we can see the full trajectory. And so I'll rerun the calculation with the new XF and XR. Not sure it was obvious to you. The basic idea that it was tilted, but because we have thrust vertically attached to the vehicle as the vehicle itself rotated, a component of what's vertical to the vehicle now kind of was off the gravitational axis, and that propelled a horizontal movement of the vehicle. So that was it. So anyways, this was kind of a fun simulation, and as I go through this, and as I went through it, I think we see what goes into flight controls, and I'd say that this kind of physical approach that I'm bringing, I'm using a tool like multi-body as opposed to what they call 6-DOF, flight models. I think it really does add a lot, and certainly we saw location of thrusters really was kind of a key to getting this right. And we even saw it with incredible sensitivity, acting in the sub-millimeter positional, at least for an open loop kind of vertical takeoff, had a big impact. So anyways, thank you.